So welcome back. We're going to learn about FDA in this class. FDA means Fisher discriminant analysis, and here we're going to deal with data with label. So we're going to do dimensionality reduction using data with some label. When we're doing dimensionality reduction with label information, it means that the ultimate goal is classification or regression because we have some labels. And when we think about PCA ignored our labeled information even if it's available. And we only calculate the sample covariance matrix of the features and computed the eigenvalues there. So it ignores all of the information about the labels, and actually the labels are not needed. However, in FDA takes into account of the label information. So we're going to use the label information, and therefore we're going to preserve the label information during our dimensionality reduction. So FDA, actually LDA is the same method with FDA, so I'll just call it as FDA. So FDA is projecting data while preserving our class separation. Let's imagine some classification problem first. And in FDA, the examples from same class are put closely together by the projection, and the examples from different classes are placed far apart by the projection. Let's see what this means in detail in the next slides. So in FDA, we're trying to do classification onto in a one-dimensional space here. Let's say that we have data points like these red and green data points here. And as we are doing FDA, you need to think that we have the label information. So we have red and green information here. And what we're going to do here is we're trying to do some classification in one-dimensional space, not two-dimensional. Currently, it's a 2D data, but however, we're going to reduce the dimensionality so we can do some classification problem in a 1D space here. So we need a 2D to 1D data projection. And we're going to do this projection onto our line omega. So here, you can think this as omega. And when we are doing some projection here, you can see that these distributions indicates the projection, the red projection and the green projection. And for example, if we had this line omega here, we can see that these projections are pretty well because these two classes are pretty well divided. So we can do the classification quite easy. However, let's see this example here. If we set our line omega to be this one, then we can see that our distributions, the projections of our data points, are really overlapped here. If the distribution is overlapped, we can't really do classification here because in a 1D space, these look the same. So therefore, this is the best line omega for doing classification, and this is one of the worst line for doing classification. And then our problem now, our question is, then how can we find this line omega? And to do this, let's do this step by step. So we're trying to do some projection onto line omega. And let's say that we have two coefficients here, omega 1 and omega 2. So this omega is a vector with omega 1 and omega 2. And what we're going to do here in the starting point is we're going to first assume that we have zero mean in our data. If you don't have zero mean, you don't need to worry. Just shift your data like this one, x minus x bar, the mean of your data samples. And therefore, what we're going to do is a projection. This y hat is the projection of your data point x onto your line omega. So omega transpose x, this equals to omega 1 x1 plus omega 2 x2, and there's no omega 0 here. I'm going to set omega 0 as 0. And now we're going to do dimension reduction, which means that we are reducing our dimensionality, which had 2D in the first place, x1, x2, to y hat, which is a scalar 1D variable. So this is 2D to 1D. So each data point x, a two-dimensional data point, is projected onto our line omega. So the projected length on omega direction. So we get a 1D length here. And for a given omega here, for a given line, the distribution of the projected points is now specified, like what we have seen in the previous slide. And now the question here, we actually know the answer. Which omega is better for classification? The better omega is where we have less overlap between the distribution when we projected our data onto our line omega. So, to calculate the line omega, we first need to talk about the sample statistics in our projected space. Our projected space was y hat, and this is omega transpose x, or this also equals to x transpose omega. And we are trying to do some classification problem with data points in class C0 and data points in class C1. So this is and also let's assume that we are focusing on a 2D problem for explaining this example. So for class C0, we can calculate the sample mean. I'll call this as mu0. Class C1, also mu1, sample mean. Sample variance S0 in class C0. Sample variance S1 in class C1. So yeah, we can calculate these as this with these equations. And in our projected space, we can do our projection using, we can project our mean and variance onto line omega using this one. Here, this is actually projecting mu onto omega. And here, this is actually projecting the data samples onto line omega here. And then we're going to get omega transpose times S0 times omega. And actually, this was what we have done in the previous lecture when we explained PCA. So if you're confused with why this happened here, just see page 20 in PCA. So here, this one indicates the sample mean in projected space. And this one is the sample variance also in the projected space. Similar to class 0, we also have the sample mean in the projected space of class C1 and the sample variance in the projected space in class C1 as here. So based on these statistics, let's try to do FDA. Let's talk about how we can do FDA now. So when we're doing FDA, we're trying to find omega so that when projected onto omega, the classes are maximally separated, which means that we want to maximize the distance between classes. Also, you want to make each class tight. So we want to minimize the variance of each class here. And we can do this using some maximization and minimization problem at the same time. For this maximization problem, we can do this maximization by maximizing this, where this mu0 transpose omega was the sample mean in our projected space for class 0, and mu1 transpose omega, this was our sample mean in projected space in class C1, and we did our squared here. To minimize the variance of each class, we can do this, where this omega transpose S0 omega is the sample variance in our projected space C0, and omega transpose S1 omega is the sample variance in projected space in class C1. And additionally, I added these two, N0 and N1, where where n0 is the number of data in class 0 and n1 is the number of data in class 1. This is to give some weights on classes with more data points. So we need to maximize this one and minimize this one at the same time. And actually, we can do this with a single maximization problem here. If we put this minimization problem in our denominator, then if we minimize this one, the total will be maximized. And in the numerator, we're going to put this, the maximum distance between classes term in the numerator as itself here. Then if we find the omega that maximizes these terms, we're going to get some good classification on our projected space. For example, if we look into this line here, let's say that this is line omega, and we can see that, and then if we do our projection onto line omega, we're going to see two distributions like these, from the blue one and the red one here. And we can see that the classes are maximally separated. They are separated very well. And inside each class, these classes are actually tight. So the variance of each class is minimized. In contrast, let's look into one example that is not that really good. In contrast, if we find some line omega like this one, we can see that there's some overlap of the distributions of the blue one and the red one. So these are not maximally separated. We can do better. Also, the class, the variance in each class is not really tight. It is widely spreaded here. So in the point of view for doing better classification, this one is better. So how can we find our line omega based on this maximization problem? So the thing that we need to solve here is this problem here. We need to solve omega that maximize this one here. So our unknown is omega, and the other terms are all something known. So we don't need to be worried. We can calculate the covariance matrix, and we can calculate the means. Everything is known. The number of data points, they are all known. So we just need to calculate this cost function, j omega, here, which is actually just simply this term here. And we're going to simplify this equation by defining some parameters like this one, variables like this one. I'm going to define m as the distance between two mean points in our classes. I'm going to define sigma as n0s0 plus n1s1, and I'm going to say that this equals to r transpose r, because we can decompose this since this sigma is a symmetric matrix. We know that our covariance matrix, S0 and S1, they are both symmetric. So sigma is also a symmetric matrix. And for a symmetric matrix, we can find such decomposition that makes sigma equals to R transpose R. And I'm going to define U as R omega. And therefore, we can also express omega using R inverse times U. So this equation, this cost function, becomes this one here. And m transpose omega square in the numerator and omega transpose sigma omega in the denominator here. Okay, so starting from this equation here, we're going to change this cost function, which was a function of omega, to a function of u by using omega equals to R inverse u, or u equals to R omega. So we can change this equation into this equation here, and this equals to U transpose U because U equals to R omega. So this is U transpose U. And here, this is M transpose omega. Omega is R inverse U. And we get this equation in the numerator. And if we also write this more simpler, we will get this equation here. So Ju, we can express our cost function now as this one. And what we can see here is, what we want to do here is we want to make this maximum. And this is maximum when U equals to A, some constant, times R inverse transpose times M. And this is because we are maximizing the inner product of R inverse transpose M and U. I'll call it as U hat, as the unit vector. So this is the same with the inner product of this one. And when we're doing our inner product, this is always maximum when U is parallel to R inverse transpose times M, this one. So therefore, this is maximum when U is parallel to R inverse transpose M. So therefore, we got this equation that U equals to A R inverse transpose M, and we know that M is mu0 minus mu1, and we know that omega equals to R inverse U, and if we calculate this one, we can finally get this form of omega, our line omega, which is a vector, including the weights of our lines, omega 1 and omega 2. So this is omega 1, omega 2, because I was explaining this in a 2D example. In 2D, this will be omega 1, omega 2, and S0, S1, these are also some 2 by 2 matrices, and mu0, mu1, these are also 2 by 1 vectors. So let's now look into an example of FDA using Python. So let's consider that we have data samples like this one. Some red and blue data samples that we want to do some classification. So these data samples have some labels, and we can generate these data using NumPy. And since we are doing FDA and we know how to calculate our line omega, this is our line omega that will maximize the separation between the clusters, or the classes, and make the variance inside the classes tight. We know how to calculate this omega that will do those maximization and minimization problem, which leads to this one. Omega equals to A n0 s0 plus n1 s1 inverse times mu0 minus mu1. And we can just simply calculate everything here as these lines. And we can obtain our weights, omega, here. And then we can do some projection and can draw some histogram here and obtain how our projections are well done. So we can actually do some classification in 1D. So this 2D problem changes to a 1D classification problem. If we use a different omega, for example, this omega, then if we do some projections here, you can see that the projections are very overlapped, which means that it is very hard to do some classification in one-dimensional space. So this omega is not a good omega. And this is also one more example for a different omega, which corresponds to x equals to 0. If we do some projection here, we're also going to see a lot of overlap as this histogram here. So this is also not a good projection to do our classification in one-dimensional space. We can also do this FDA very easily using Scikit-learn. We can import discriminant analysis for FDA from Scikit-learn, And this is our classification model. And here we're going to use linear discriminant analysis, which is the same with FDA. And if we fit this, we're going to be able to obtain our line omega, LDA projection line, LDA classification boundary. So this line is omega, and we can see that our classification can be done really good using this line omega here. So this is the demonstration of FDA from Colab. So I'm going to briefly just demonstrate it because I explained the details in our slides. So to run our Python code, I'm going to first import the libraries NumPy and Matplotlib for doing our FDA from scratch. And we generate our data using this one. And then we're going to calculate our omega from this code block here. Please try to do these by yourself and try to code FDA from scratch. So here, this is how we calculated omega. This is what we derived from our maximization problem. And by this omega, we are able to calculate our weights of our lines that will be good when we have some projection of our data points, so we can have good 1D classification. So we can also do some post-processing of the projection line and histogram like this one. And if you run this one, you're going to see our projection line. It's very good here. We can see that these are well separated, and it's type of each class. And by drawing the histograms here, these are the projected data histograms, and we can see that these are well separated also. And the examples that we looked into when we had some different omega line, we can also calculate these ones. For example, if this was the x-axis, like y equals to 0, then we're going to have a large overlap of our histogram. And for different omega on y-axis, x equals to 0, we're also going to see a large overlap inside our histogram. So these are not really something good for doing our classification in one-dimensional space. And the last, this is for the Scikit-learn code. What we need to do is just simply reshape the data and then import LDA or FDA inside Scikit-learn and load that as your classification model and fit that with our data points. And then you're going to be able to do FDA very easily. You can see the histograms here, which are well separated. So we can do classification also in this one-dimensional space. And to extract the information of the classifier boundary, you can also do something. Run this code here. And to extract the projection line information, you can calculate this one here. So, and last, if you want to do some good post-processing, even from your Scikit-learn function, you can draw your projection line and classification boundary both on a single graph with your data points. And you're going to get this plot as you saw in the slides that we explained in the previous minute.